Welcome to Study Loop.
Here we are asked about the first ionization energy, and the exception to the periodic trend of it and why they occur. So the ionization energy is the energy that is required to remove one electron from an atom. Okay, so like we know that the trend of it is the same as the trend for the periodic for the atomic size, because when the size becomes smaller, that means that the effective nuclear charge experienced by the electron also increases, and that makes the ionization energy to increase. So since the size decrease across the periodic table, that means that the ionization energy is going to increase across the periodic table. So ionization energy, it increases from left to right across periodic table. But there are some exceptions to this trend. So I'll just discuss some of these exceptions. One of it is when you compare the beryllium atom ionization energy to the boron atom ionization energy. So beryllium is the fourth element on the periodic table, and the electron configuration is 1s2, 2p2. And boron is the fifth element on the periodic table. Electron configuration is 1s2, 2p3. Okay, so we expect the ionization energy to increase from beryllium to boron. Oh, sorry, I made a mistake in writing that electron configuration. So 1s2 and then 2s2. Then we'll have 1s2, 2s2, 2p1. So this is atomic number 5 and this is atomic number 4. Okay, so we expected the ionization energy to increase from going from beryllium to boron, but what we observe is the opposite. The reason is this: if you look at the s orbital, if you draw the orbitals just like this, so this is 1s and this is 2s. So you have 2 electrons in 1s and 2 electrons in 2s. If you draw that for boron as well, so 2, 2, 1s, 2s, and this is 2p. 2p has 3 suborbitals, the px, py, and the pz. So this is 2p. You have just 1 electron in it. So for boron, for beryllium here, the orbitals are completely filled. That is, the 1s orbital can occupy a maximum of 2 electrons, and the 2s orbital can also occupy a maximum of 2 electrons. So the orbitals are completely filled. But when you come to the boron, 1s orbital is completely filled, 2s orbital is completely filled, but the p orbital is having just 1 electron in it. And this will lead to the destabilization of the p orbital, so the energy is going to be high, and that will make the boron to be higher in energy than the beryllium. So it will be easier to remove this electron from the 2p orbital of boron compared to removing an electron from the 2s orbital of beryllium. So that is because of the completely filled 2s and the 1s orbital of beryllium, whereas here the 2p orbiter is not completely filled, and it is not even half filled. So this electron is easier to remove when compared to the electron in the beryllium. Another reason or another way to think about this is to think in terms of uh, the effective nuclear charge. So here you have 1s and 2s orbiters. Here you have 1s and 2s orbiter, and the electron that is available paired is the 2p. So you have screening from this 2s, and this is not experiencing the same effective nuclear charge as is experienced by the 2s and the 2s here. So this becomes easier to remove. Another exception is when you look at nitrogen and oxygen atom. Nitrogen is 7, oxygen is 8. So you write the electron configuration 1s2, 2s2, 2p3. And oxygen is 1s2, 2s2, 2p4, right? So the p orbital here is completely filled. It's partially filled, I mean. Here you have 1, 2, 3. And here you have the p orbital to be 1, 2, so 1, 2, 3, 4. So the p orbital here is partially filled, and that makes it to be more stable and relatively difficult for the electron to be removed from it. Whereas the p orbital here is not partially filled, and it is not fully filled, so it is less stable, and electron can easily be removed from it. Another way to think about this case is that here you have the electrons occupying the p orbital singly, whereas you have um, two electrons that are paired here. So whenever you have two electrons together, because the electrons are the same charges, the negatively charged electrons are coming together, that will create repulsion. And the repulsion will lead to the destabilization of that energy, of that orbiter or that electron, and which will make it easier to remove. So the expected trend is when we are going from nitrogen to oxygen, we expect the first ionization energy to increase, but it is the opposite because of this phenomenon where we have paired electron in the oxygen that leads to repulsion and leads to a decrease in the ionization energy of the oxygen atom relatively comparing to that for the nitrogen atom, and also because of the uh, outfield that leads to stabilization of the p orbital of the nitrogen relative to the p orbital of the oxygen, which is not half filled and not fully filled, that leads to the destabilization of the p orbital of oxygen. So this leads to a decrease in the first ionization energy when we are going from nitrogen to oxygen. So uh, these are some of the exceptions to the ionization energy trend on the periodic table.